Hello and welcome to this video about sound intensity and resonance. In this video we're going to look at what sound intensity is and how to calculate it, how we measure relative sound intensity, and what is resonance. So we're going to talk about intensity of sound, and to do that let's think about a piano. And when the hammer inside the piano strikes the wires right here, those wires start to vibrate, and those vibrations of the wires are transferred to the piano's soundboard, which then vibrates also. And the vibration of that soundboard exerts a force on the air molecules around it, causing those to move as well. The soundboard, in essence, does work on the air because that force is exerted through the actual displacement of the soundboard as it vibrates back and forth. So the soundboard's kinetic energy is converted into sound waves. And those sound waves, remember, are longitudinal or compressional waves. They are going to travel outward from the source of that soundboard. And as they do that, the energy is going to be transferred from air molecule to air molecule to air molecule. And we call the rate at which that energy is transferred in a particular area the intensity. So intensity of a sound wave is going to be the rate of energy transfer divided by the area. And remember that the rate of energy transfer is power. And if you'll also remember that power, the SI unit for power is the watt. So our units for intensity are going to be watts per meter squared. Remember also that our sound waves are spherical. So the area in this formula is going to be the area over a spherical surface, which is 4 pi r squared. So here's our formula for the intensity of a spherical wave. It's going to be equal to power divided by 4 pi r squared, r being the distance from the source. Let's do a sample problem together. Let's say that the intensity of sound from an explosion is 0.1 watts per meter squared at a distance of 1 times 10 to the third meter, about 1,000 meters. Find the intensity of the explosion at a distance of 5.0 times 10 squared meters. That would be about 500 meters. We know that when the radius is 1,000 meters, the intensity is 0.1 watts per meter squared. We'd like to find out what the intensity is when the distance away from the explosion is 500 meters. So how are we going to do that? Remember that power, or intensity, equals power divided by 4 pi r squared. And so we can find the power of this explosion. That's the rate of energy transfer. When we know what the rate of energy transfer is for this explosion, the power, we can then find out what the intensity would be at 500 meters away. So I can plug the values in for the intensity and for my radius, and my equation will look like this. I can then solve for the power. The power is simply going to be 0.1 times 4 times pi times 1 times 10 to the third squared. And that ends up being 1.26 times 10 to the sixth watts. Now I can use my same equation for intensity, and instead I can plug the values in for power and for my radius being 500 meters. And I can simply plug these numbers into the calculator, and I get a value for intensity of 0.40 watts per meter squared. Now, does this answer make sense? Well, when I'm 1,000 meters away, I have this much intensity, 0.1 watts per meter squared. If I am only 500 meters away, I would expect there to be more intensity. And indeed, there is 0.4 watts per meter squared, so that makes sense to me. This is just a picture showing an explosion of a steam line in New York City in 2011. And it happens to be roughly 1 megawatt of power. And that is, when we calculated 1.26 times 10 to the sixth watts, a megawatt is 1 times 10 to the sixth watts. So our power in our little made-up explosion is roughly equal to 1 times 10 to the sixth watts, 1 megawatt, which is about what that explosion, the power of that explosion is as well. So what determines whether a sound is audible? Remember we talked about frequency being a determinant factor, and that human hearing ranges from 20 to 20,000 hertz as far as frequency goes, but intensity is also very important in determining whether a sound is audible. As you can see on the graph, sounds at really low frequencies, below 50 here, or really high frequencies over here, have to be fairly intense to be heard. Whereas in the middle of this spectrum of different frequencies, audible sounds are audible at much lower intensities. The softest sounds that average human ears can hear is at a frequency of about 1,000 hertz and an intensity of about 1 times 10 to the negative 12th watts per meter squared. This chart happens to be in centimeters squared, but 1 times 10 to the negative 12th watts per meter squared is right about here. That is called the threshold of hearing. Some people can hear sounds softer than that, but this is the average, the threshold of hearing is for the average human ear. The loudest sounds that the human ear can tolerate, they have an intensity of about 1 watt per meter squared, and that's equal to 10 to the negative 4th watts per centimeter squared on this graph. And you can see right here, that's called the threshold of pain, because sounds with greater intensities than this can produce pain in addition to hearing. And exposure to sounds above the threshold of pain cause immediate damage to the ear, even if no pain is felt. Prolonged exposure to sounds of lower intensities can also cause damage to the ear. So remember, the frequency of a sound wave determines its pitch, and the intensity of a sound wave determines how loud the sound is. Volume, however, is not directly proportional to intensity. When we have a sound that is twice the intensity of our very faintest sound at the threshold of hearing, it is not perceived as being twice as loud. That's because the sensation of loudness is approximately logarithmic to the human ear. Therefore, a relative intensity scale has been set up called decibels, and we abbreviate that lowercase d, capital B. And decibels, this decibel scale is found by relating the intensity of any given sound to the intensity of sound at the threshold of hearing, and that's set at 0. And because it's a relative scale, it's dimensionless. There are no units because it's relating one intensity to another. This table shows the conversion of intensity into decibel levels. And when we multiply the intensity by 10, we add 10 decibels to our decibel level. And so a difference in 10 decibels means that the sound is approximately twice as loud. Because the volume doubles each time the decibel level is increased by 10 decibels, sounds at the threshold of pain, down here at 120 decibels, are 4,096 times as loud as sounds at the threshold of hearing, 0 decibels. So remember that the frequency of a pendulum depends on its string length. And every pendulum vibrates at a certain frequency. It's a natural frequency, depending on the string length. Resonance is a condition that exists when the frequency of a force applied to a system matches the natural frequency of the vibration in that system. And let me give you an example because I think it's easier to understand. Let's say we have 4 pendula hanging here, and they're all with these different string lengths. However, if we have these 2 pendula that are exactly the same string length, and we set one in motion, and it begins to oscillate with a particular amplitude, eventually this pendulum will also begin to oscillate. Some of that energy is going to be transferred to this pendulum because since both of them have identical string lengths, they both oscillate. They both have the same natural frequency. So one of them oscillating is going to begin to set the other one into motion as well and transfer some of that energy to it. That is called resonance. An example of structural resonance is our Tacoma Narrows Bridge in Washington that collapsed in 1940 because there were very high winds, 40-mile-per-hour winds, and when those gusted violently, the bridge began to twist and vibrate because those winds happen to be transferring energy at the same frequency as the natural frequency of this bridge. So one way resonance is used is to amplify sound in an instrument. We have two different kinds of vibrations, force vibration and sympathetic vibration. A force vibration will be the tendency of an object to force a connected or joining object into a vibrating motion. For example, we have our vibrating guitar string, and it's been plucked and it's vibrating. It forces the guitar bridge to vibrate. Those are a touching and a joining. That in turn forces vibrations in the guitar body. A sympathetic vibration would be force vibrations that are due to objects possessing the same natural frequencies and being near each other but not touching. So when those vibrations in the guitar body are transferred into the air, those are the sympathetic vibrations, and when those are transferred into the air, the guitar body has a larger area than the string alone, and so that enables the vibrations to be transferred to the air more quickly than just a single string, and so it increases the sound intensity. If you were to pluck this string without it being attached to the bridge and to the guitar body, it would not be a very loud sound. So how does the human ear work? How are sounds heard in the ear? Well, we have three parts to the ear: the outer ear, the middle ear, and the inner ear. The outer ear obviously collects the sound waves, and those are allowed to proceed down the ear canal, which terminates in the eardrum. The eardrum vibrates when those sound waves hit it. It transfers those vibrations to the inner ear right here, and the inner ear is made up of three tiny bones called the hammer, the anvil, and the stirrup, and those in turn vibrate and transfer the vibrations to the inner ear. In the inner ear is a tiny snail-shaped organ called the cochlea. And the membrane of the cochlea has different natural frequencies in different places. It's called the basilar membrane. And sound waves that have different frequencies are going to resonate at different spots along this membrane. And that then creates impulses in different nerve fibers. Those impulses are sent to the brain, which interprets them as different frequencies of sound. So you can see how important the concept of resonance is in our own hearing. Here are a few advanced ideas. This is just a picture of the inner ear inside the cochlea. The cochlea has fluid and little tiny hair cells inside of it. And some advanced ideas, though. What are some common causes of hearing loss? What are some advances in medicine that are trying to treat different hearing disorders? What was the original unit of the decibel? Was the bell? Who was it named for? Can you find other interesting historical examples of structural resonance? Try the conceptual challenges in your textbook. Any other ideas you might have would be great to see, and I look forward to seeing you in class.